All right, thank you for the introduction. It's great to be here. I've enjoyed this conference quite a bit. It's been a nice variety of topics, angles on monitoring. So I'll speak about some of the statistical questions that arise in distributed tracing. So in one sense, the questions that I'll talk about are somewhat narrow, but some of the themes that arise are hopefully of a more general interest. So just a brief introduction. So my background is in pure mathematics. I used to do research in algebraic geometry. After finishing a postdoc at USC about 5 years ago, I decided to join the tech industry. I've been at SignalFx for about 3.5 years. So we're a real-time streaming analytics platform for monitoring and alerting metric time series. And we've recently announced a distributed tracing solution that leverages that, as well as some other things. So as I mentioned, the main goal in this talk, or the main goals, are to really isolate some of these statistical problems and hopefully present some frameworks for thinking about them and maybe some answers or solutions. So the main question that distributed tracing is trying to answer, in my opinion, is how does work flow through a microservices architecture? And so when you compare the sorts of data that arise in distributed tracing to something like logs or metrics, say, the model is somewhat less flexible. So spans and traces are required to have a particular format, whereas logs and metrics can be sort of anything, like you're an observer, this is what I saw, I took a measurement, or I logged that something happened. But the information you get from spans and traces is much more contextual. So probably some of you have seen a trace before, maybe some of you haven't, I don't know. But I brought one with me. So it's not under your seat, it's on the screen. So I hope you're blown away if this is the first trace you've seen. So the horizontal axis is time. Each bar represents a span, so a service and an operation. And the length of the bar tells you how long it took. And we also encode parent-child relationships. So sometimes a span calls some other span, and that's represented by a thin black line. And in this coloring, the bars are colored by the service that's involved in doing that work. So as you can see towards the top, the purple guy is doing a bunch of stuff. So this is the REST layer staring at itself. And then eventually it says, I need to talk to the analytics engine, and she gets involved. And then the analytics engine has to talk to the query handler, and then that talks to a few databases. So in the end, I think 5 or 6 services are involved, and you can see how the work is kind of flowing through at a fairly detailed level. Okay, and then if you don't like this level of detail, here's the whole thing. It's somewhat informative if you know something about this system. But anyway, the data model is basically as follows. So a span consists of a start time and an end time, the service that did the work, and the operation name. So there's also some accounting we have to do. So we have to have an identifier for that span, the identifier of its parent, so long as it's not the initiating span, and the identifier of the containing trace. Okay, and a trace is nothing but a collection of spans with the same trace ID. Okay, so note that a span has an end time, but actually a trace does not. And so when thinking about these data sources, one problem that arises, I would say somewhat independent of the architecture, is a data volume problem, which you could also think of as a relevance problem. So you have very many endpoints, they're executed very many times. How do you decide which traces you should keep? And so when I say which traces you should keep, I'm already kind of making an assumption that we should do the selection process at the trace level. This is usually called coherent sampling. There are also variations where you are allowed to just select some spans from a trace, and the fact that you select one span from a trace does not require that you select all of the spans from that trace. For simplicity, I'll assume we're in the so-called coherent paradigm, where once we've decided to keep one span from a trace, we'll just keep the whole thing. But many of the ideas apply equally well to the incoherent setting. And of course, when you have names like coherent and incoherent, it's hard to pick the incoherent one. But but it's out there. That's not my terminology, by the way. So let's talk a little bit more about some approaches to this core question of how to decide which spans or traces we should keep. So one approach is usually called head-based sampling. And the idea here is that you pick a number, like 0.01, like that's a number, and then you keep a trace, you keep every trace with that probability. So you keep 1% of the execution traces that happen in your system. Okay, you could also express this as a rate if you want to be a little bit fancier. So I'm going to keep a certain number of traces per unit time. Okay, so this has some advantages. So one thing that's good about it is that it's very simple to implement. So there's essentially no statistical algorithm in your code. It's fairly easy to distribute. Like if you have a lot of machines doing this sort of work, they just all have to know what the probability is. Not a very complicated communication problem. I would venture to say you could even do this without a data scientist. So the resource requirements are very low. So because you can make the decision on the head on the initiating span, you don't have to keep around a bunch of data because it might be selected later. So once you've decided to keep something, you just have to remember to keep all the spans with that trace ID. And if you decided to discard something, well, who cares? And you don't have to do any calculation. So it's somewhat light on the resource requirements. And it's also easy to reason about. So if you take a uniform random sample from some population or from some distribution, then any statistic you calculate on that is correct in expectation. And it's also somewhat straightforward to calculate confidence intervals for those statistics using things like the central limit theorem and some other ideas which I may mention a little bit later. Okay, so that's what this uniform random sampling has going for it. What it has going against it is that most of the time, hopefully, stuff is sort of working, and the executions that you see are fairly uninteresting. Like a user is just asking for some data, and you are providing it to them, and you sort of go on with your day. And the fact that there is a problem in a trace or a span is not always present when the trace arrives. It's usually not. So I found some example. You'll have to use some fine motor ability now and slide over here. Can I do it? Where am I? So yeah, this basically proves I can embed video in a Jupyter notebook. So I don't know if you can read that. I can't. Anyway, there's some endpoint. And it's making some calls. It's there's some asynchronous calls it's going to make. Let me hit play. There are many copies of essentially the same call structure. And so I open the trace, and everything is looking great. It's totally fine. Like, don't worry about it. But oh my God, there was an error. Okay, and it also took a really long time. So, if you keep 1% of traces, like maybe you'll catch this person, or maybe not. But this is probably more valuable than those many traces where nothing interesting happens, and you might want to show some preference for this. And to do that, you'll need something that's tail-based, which means that you will not make a decision when something arrives, but rather you'll defer the sampling decision until the time that the trace has completed, and then show some preference for the interesting ones. Okay, and now we're allowed to have some opinions and feelings about what makes a trace interesting or anomalous, and then it's my job to turn that into some formulas. So what are some aspects of a trace that might be interesting? So latency comes to mind. So how long does this operation typically take? How long does this endpoint typically take to complete? So errors are usually interesting, so especially when you compare it to, say, the typical error rate for some endpoint. The frequency of execution, so just simple retrieval calls usually don't have any interesting structure, but there may be some relatively infrequently exercised endpoints that have larger workloads behind them where more stuff can go wrong, and you want to show some preference for those. And then some aspects of the structure of the trace. So for example, given given that this operation is occurring in this trace, or for this endpoint, what is the distribution of latency? Are there any interesting conditional distributions? And so the challenge is to develop some principles for a tail-based sampling scheme that preserve the virtues of the head-based scheme. In particular, we'd like to be somewhat resource aware, and we would like to be able to calculate our summary statistics in an accurate and understandable way, while maintaining the ability to have a preference for the anomalous, so-called interesting traces. Okay. Any questions right now? Okay, we can have more questions at the end. Okay. So let me just give I think in cartoons, and so here's a sort of cartoon of an approach or an algorithm. I increased the font size. I hope you can see it. I increased it since I did the AV check. So I have this great web app running. It's got 3 endpoints. My users get things, they create things, and update things. Get is very common. It receives about 1,000 requests a minute, and its median latency is 300 milliseconds. Create receives about 100 requests a minute. Its median latency is 400 milliseconds. Update is the rare one. It only gets 10, and the median is 500. So now let's say I have a budget to keep 30 traces every minute. So the first step is to divide up that budget among the endpoints, showing a preference for the infrequently used endpoints. Okay, so I've got 30. I'm going to spend 15 on get, 10 on create, and 5 on update. And then within each endpoint, I'm going to show some preference for those traces that take longer than they should. So my strategy will be to keep, for get, about 3 under the 300 millisecond threshold and 12 over the 300 millisecond threshold. And I have a similar way of dividing up the budget for the other endpoints. Okay? And we could do something similar for errors, but just for simplicity, I exclude them. Okay, so the general sketch is to form forecasts for volume for each endpoint, which you can think of as a multivariate forecasting problem, which I won't really say too much more about. Forecasting is its nice own subject, which could be treated separately. Then periodically, every minute, say, divide up some given budget among those endpoints with a preference for the infrequently used ones. And then within the periods, perform a bias selection. Okay. So let's talk about budget. So how do you divide up a budget of B per minute among n endpoints, assuming that the ith endpoint receives BI requests per minute? So here are 2 extreme proposals. So the first one is to do equal allocation without regard for volume. So everybody gets 1/n of the budget. Okay, that's the first bullet point. And the second one is to do it proportionally according to the volume. Okay, and so here's a chart of that. So the horizontal axis is the proportion in nature, and then the vertical axis is the unnormalized proportion of the budget allocated. Since the sum may not be 1, you have to divide by the sum to get another point on the simplex. So I don't know. Hopefully you can see it. The blue line is the Senate, and the red line is the House. And those are institutions that seem to be working pretty well. And another institution that works well is a sort of hybrid approach where you don't do it equally, you don't do it proportionally, you do it somehow in an intermediate way. And more formally, this involves choosing a concave function and then applying that concave function to the observed proportions and then normalizing. Okay, so what does this get you? Well, if you have a data set of traces, each of them picks out a little chunk of the dependency graph in your microservices architecture. And then if you have a bunch of them, you can take the union of these and visualize the dependencies in your system as a whole. And you can imagine that if you show some preference for the infrequently executed endpoints, that you see more of this graph, maybe you see more of the structure. And so I've done some experiments. So this is some dependency graph constructed on a set of traces obtained from a head-based sampling approach where we fix a probability. Okay, so you get some graph. It looks great. On the other hand, if you show a preference for infrequently exercised endpoints, you see actually a new service, which I found somewhat alarming. Of course, a dependency relating to that service, and a dependency between two services, which you knew about in the previous slide, but which only shows up because there was some endpoint that actually realized that dependency. And so you can probably imagine that if you decorated this with some alerts, it might be good to know that these purple and yellow services had a dependency between them. Okay, so that's it for budgeting. Now we can move on to some more statistically oriented discussion. So one thing we'd like to know is, how unusual is it for an operation or endpoint to take a certain amount of time? And to answer that, we should have a data structure that has some properties. So it should support percentile queries. It should be neutral in the sense that the things it picks should not influence the way it calculates percentiles. It should have a notion of time. So those are sort of the qualitative statistical properties. And then, of course, the engineers would like it to be small, mergeable in case it's split among many machines. And updates should be very fast when a new data point arrives. It should be incremental. Okay, so now let's think a little bit about, let's have some more graphs. So if you don't have a data structure like this, then you can still sample as a function of the rank of your trace as it fits into the appropriate distribution. Unfortunately, that function has to be constant. So this is a fascinating graph. If you maintain also the median, and maybe you do it in some exponentially weighted way, then, for example, you could show a slight preference for traces whose durations are longer than the median relative to those that are shorter than the median. And if you have the whole thing, well, then you can do something that is much smoother. So you can vary the probability of being retained smoothly as a function of the rank of the example in its distribution. And so if you kind of stare at the green curve, pick a point where pick the point where the value is 0.8 versus where the value is 0.2. That's saying a trace that lives in this percentile is 4 times as valuable as one that lives in this percentile. And there's kind of a similar thing you can do for errors. It's actually easier because you're dealing with counts rather than distributions, so I won't discuss the details. But this is just some way of thinking about sampling as it relates to histograms or distributions. And by the way, all of these have the property that their integrals are 0.2, which is to say that they would all sample at 20% in expectation. Okay, so what does this get you? So again, I have a comparison. So if you use a head-based approach for some data set, you receive the following distribution. Okay, so it's some distribution. By the way, both axes are logarithmic. And then if you show a preference for those traces that took longer than expected, you get something that looks quite different. So I don't know if the tick marks are perfectly aligned, but if you just stare at the 1 second mark, you can see that there are only a few on the top, but there's much more blue stuff on the bottom. That's to the right of 1 second. Another thing I would like to note is that the chevrons, which indicate the 50th, 90th, and 99th percentiles, are in basically the same place, even though there is way more than 1% of the blue stuff, even when you account for the logarithmic nature of the axis, to the right side of the red mark in the bottom one. And that's due to an accounting trick, which I'll discuss in a minute. So note that even though the distributions are quite different, the percentiles that we calculate, even on the biased sample, basically agree with the representative sample. Okay, and there's also a similar story for errors. So look, it's not very red. Oh my gosh, it's so much more red. Okay, so I know the question on everyone's mind is, well, that sounds good in practice, but how does it work in theory? So So I never attended the University of Chicago, so I feel like somewhat of a phony for using this, but in my defense, I recently attended another talk where a speaker who was also not from the University of Chicago used this line. So it's a little bit phony, but it is at least also unoriginal. So a quick comment about percentiles versus other ranking devices. So if I can just throw up a straw man briefly. So the data structures that can calculate percentiles tend to use up quite a bit of memory and then require some CPU. So why do we bother with this? Why not just keep something like the rolling mean and standard deviation and then compute the retention likelihood not as a function of the percentile, but instead as a function of the z-score, right? The number of standard deviations from the mean, right? And maybe do this in an exponentially weighted way. Okay, so what does this have going for it? Well, let's say we have two observers. One's computing on x, and another one is computing on ax plus b. So you can think about Fahrenheit and Celsius. So if they do this, they'll compute the same z-scores. Right? So when you're in a Monitorama in Amsterdam, you don't say what temperature it is. You say, gosh, it's 2.5 standard deviations above the seasonally adjusted moving average. I'm going to wear shorts today. Right? That is a language that everybody understands. But unfortunately, there's also a third observer who's computing on the random variable exponential of x. And she will compute quite different z-scores. And this is actually very uncool. It is not really possible to reason about how many traces you would keep on average if you are operating in the space of z-scores. So of course, it's better than operating on the distributions, but it's still not quite enough. And so you need a little bit more. So here are some example data structures which can facilitate this process. So the first one is usually called an exponentially decaying reservoir. And the idea is basically that you maintain a sorted list of durations, say, where the probability of being in that list is a function of time. And you're less and less likely to be in that list as you get older and older. It's a kind of special case of weighted reservoir sampling. So there's another structure which is quite interesting called a t-digest. And so it's sort of a dynamic histogram. So a histogram usually requires the specification of a bunch of bins, and then you just count how many examples you see in each bin. So for the t-digest, you don't have to specify the bins in advance. Instead, you specify a so-called scaling function, which tells you how much accuracy you want at each percentile. And generally, the default behavior is that you are very accurate towards the tails. So your estimates of the second and 98th percentile are very good, whereas your estimate of the median is a little bit iffier, but maybe you don't care about that. So it's a kind of a dynamic histogram structure. And the last one I'll mention is based on the method of moments. It's the moment-based quantile sketch. So I said the z-score is not enough. So the z-score is calculated from the mean and the standard deviation. Of course, there are higher moments. And if you know enough moments, you can recover the data set by polynomial interpolation. And then you can calculate all the order statistics. So don't do that. Like if you're going to calculate all the moments, just keep the data set. But the idea of the moment-based quantile sketch is that, well, instead of keeping just the first two moments, maybe keep a few more, and also keep some logarithmic moments. And then once you have that information, you can estimate, you choose among all distributions having those moments, the one with maximum entropy, and then use that to compute percentiles and use that to estimate ranks. So this has some nice properties. So because it's based on closed formulas, it's somewhat easier to merge, but the error is a little bit harder to reason about. Okay, so I want to return a little bit to this. There we go. To this question of why do the chevrons align? So generally we don't want the summary statistics that we calculate on an intentionally biased population. We don't want to do that. We'd want instead to calculate on something that reflects the steady state. And so one thing we can do is just emit the data structure that is doing the ranking. as some type of metric. Another thing we can do is record the probability of sampling when we decide to keep a trace. Okay, so there's an experimental framework. So there are basically 2 players involved. The first player spits out examples from some distribution and also records the true distribution. The second player is called the sampler. The sampler keeps a biased sample, say of 10%, and records the weight as 1 over the sampling probability. And then we see to what extent they disagree. Okay, does this make sense? Okay, so the generator's view is something like this. Okay, I chose a normal distribution, but it doesn't matter that much. Okay, a fascinating blob of red. So what the sampler decides to keep looks like this. So as you can see, there's a strong preference for things that lie on the right side of the distribution. Okay, good job, sampler. When you take into account the weights, the sampler's view is this. So I don't know, it's pretty good. You show this to a product manager, they say, I don't know, it's pretty good. What do you think? Well, let me get back to you in a couple weeks. So to measure the difference between these distributions, so there are many methods. One method is to use the so-called relative entropy or Kullback-Leibler divergence. And this basically says how much information would be lost if I went from the full true data set to the sample. Okay, and there's a formula for it. So if you have random variables, capital P and capital Q with associated densities, little p and little q, it's this expectation with respect to P of the log of P over Q. Okay, so don't worry about the formula. Let's just think about its properties. So one is that it is transformation invariant. So if you apply a monotonic transformation to the x-axis, this quantity is preserved. That's cool. It's non-negative. Okay. It's not symmetric, by the way, maybe more of an anti-property. And when P and Q are the same, it's 0, right? Because the log of 1 is 0. So how large it is kind of tells you how far these 2 distributions are from each other. Okay, and so then you can calculate this on the full data set and the weighted sample, and you say, okay, my answer is 0.003, and your product manager says, well, is that in bits or nats? But actually, the product manager says, like, what the hell are you talking about? And so what you need to do is come up with some kind of baseline. So what you can do is, as a baseline, see what the divergence is between the full data set and a data set sampled uniformly at random, right? So, so compute that, and then compare that to the divergence between the full data set and the data set sampled not uniformly at random, with this focus on the right-hand side. Okay. So one thing is that this quantity depends on the sampling rate. So when the sampling rate is 1, these are the same distributions, so the divergence is 0. But generally, what you find is that the distributions of the weighted rate R sampled set is very similar to the distribution of the unweighted set. Okay. And by the way, another thing you can kind of infer from this is that the confidence intervals that you obtain when you calculate percentiles, for example, on the weighted data set are very tight towards the right side of the distribution and a little bit wobblier on the left side of the distribution. Okay. So I'm basically out of time. The one thing maybe I'll mention is there's this fascinating, there's another approach to this problem where you view the collection of traces as determining, say, a matrix of counts. So trace 1 involves service 1, operation 1 once, service 1, operation 2 once, and then a bunch of things don't appear. So you get some very sparse matrix. You can use this to define a distance function between traces, and that opens the possibility of defining clusters, which is basically a partition of the metric space where the distances within a cluster are very small, and the distances between clusters are relatively large. And then once you have this structure, you can kind of sprinkle the things you want to retain evenly with respect to that cluster structure. So maybe your traces look like this, and then if you get to keep 5, you do something like this. Okay, so this is a somewhat different approach, which does not take into account it's not dynamic stratified sampling, but instead uses an incremental clustering approach. Okay, so I have a slide of references, and I'm about a minute over, so thank you for your time.